Good evening, everyone, and welcome back to Health Ed 295. I know I've spoken with some of you individually, but I hope that everyone has continued to remain healthy and safe. Also, your family and friends as well. I know we're going through a very unusual and chaotic time, but just want to hopefully wish all of you well and that you're staying safe and protected. Um, Today, we're going to kind of switch to talk about how we interpret data. Up until this point, we'd focus on just kind of the background of EPI. Then we moved to talk about different types of study designs, from observational types of studies to our most recent lecture. We talked about interventions or um, some type of randomized control trial. Um, what we haven't talked about is actually the different issues that come up when we're interpreting um, data from studies, when we're trying to use the study designs to basically help us to make inferences, and how to be critical when we're actually looking at results. So today is broken up into two parts. The first part, we're going to focus on measures of effect, which the measures of effect that we're going to focus on in this particular class we've mostly covered, but and so some of this will seem a little bit familiar to you. Then we're going to switch to talking about different types of biases and issues that arise when we're interpreting data. So, the learning objectives specifically for measures of effect, we're going to explain the meaning of absolute and relative effects, calculate and interpret risk difference, and then we're going to discuss the role of statistical tests in epidemiologic research. So, effect measures, they quantify the measures that affect of a factor on the frequency or risk of a health outcome. And some of the measures of effect that we've used so far are relative risk, odds ratios. Those are measures of effect. And the one that we use, or our most appropriate one, will be based on the study design itself. So an example would be, how much of an effect does packed cigarettes smoked over 20 years have on the risk of developing lung cancer? And so this could be a retrospective case control study that we design, and we want to look back to calculate to see the odds of actually developing lung cancer based on X amount of packs of cigarettes smoked each week over the course of 20 years. And we'll look to see if there's an association. Um, Measures of effect can be absolute or relative. So relative risk was what we talked about during our cohort study design lecture, which was the last time we actually met in class. Then we can have absolute or attributable risks. So attributable risks are also known as rate difference or risk difference, which we're going to go over a little today. So risk difference is defined as the difference between the incidence rate of disease in the exposed group and the incident rate of disease in the non-exposed group. And this is just a very simple formula. You just basically subtract. It's just simple subtraction. So we're doing a difference between the incidence in exposed versus non-exposed group. So an example would be looking at women younger than the age of 75 in 2017 for incidence of hip fractures. So the incidence of hip fractures per 100,000 in the winter was 0.41 among the exposed women, whatever the exposure would be in this case, it wouldn't really matter. And then the incidence rate for hip fractures per 100,000 thousand in the winter among the unexposed group was 0.29. So the difference would just be 0.41 minus 0.29, which would give us 0.12 per 100,000 is the risk difference between the exposed versus the non-exposed group. Two statistical measures of effect that we're going to focus on today are p-values and confidence intervals. we've talked, or these have come up a little bit, not confidence intervals, but I've always, when we're interpreting odds ratios or relative risk, I always have you all assume that it's at the zero point zero 0.05 p-value. I don't dive too much into that because some of this will get covered or will get covered in the statistics class, but I don't I don't want to overwhelm you all with kind of going into the nuances of that, but just kind of so that these are things that you look out for when you're actually interpreting results in a study. So, no hypothesis should look familiar. Remember, when you have a hypothesis, you're basically thinking that some exposure or by giving some group an intervention is going to have a different effect compared to the control group. If you didn't think that going in, it's not a study that should actually take place because there will be no point. But in addition to that, we always have this, what we call the null hypothesis, which is basically that there's no difference between receiving the intervention and not receiving the intervention, or being exposed versus unexposed has no difference or no effect on the likelihood of developing some type of outcome or disease. So it's just important to kind of remember that there's always your hypothesis of why you're, think about the scientific method. We always have this hypothesis, which is our alternative hypothesis, but there's always going to be this null hypothesis, which is basically saying that what you're proposing is not true and there's no difference between those. So we've always assumed a p-value of 0.05 throughout this class. The p-value usually it's not higher than that, or what someone would set in a study, but they definitely can look at a p-value of being lower. So for some studies, they might, set the p-value at 0.01 or below, or 0.001 or below. And by definition, it indicates the probability that the findings observed could have occurred by chance alone. In terms of there being a non-significant p-value, meaning that it would be a p-value that's above 0.05, so 0.08 or even 0.059, which becomes very controversial because some people interpret that as it's so close to 0.05, so what do we do with that? But in general, we would just assume anything above 0.05 would be considered not significant. So for studies with small sample size, the sampling error may be large, which can lead to non-significant tests, even if the observed difference is caused by a real effect. So this is why sample size becomes important. Doing the appropriate test becomes important. All these things actually interfere with your results or their interpretation of your results. So it's just really important when people are statisticians and researchers, when they're designing studies and setting up their analyses, that they really vetted everything out and making sure that they have the right things in place and have done their research or background research. Then we have confidence intervals, which I haven't talked about in class so far, but it is something that's important. So a computed interval of values that with a given probability contains the true value of the population parameter. What does that mean? So basically, just say, for example, we've calculated relative risk last time we met in class when we were talking about cohort studies. We got one relative risk, and maybe let's just say, for example, we got a relative risk of 2. And we would interpret that as, compared to people who were unexposed, those who were exposed had 2 times the risk of developing our particular outcome of interest. You would actually not just get that 2, you would get a range. And so that's what we call a confidence interval. So if you actually put this, you will run what we call a modeling in statistics. You would do your analyses. It wouldn't just give you 2 as a relative risk. It would probably give you a range, just say, for example, a range of 1.5 to 7.9, for example. And so that will be our confidence interval. And then we would really interpret it as we're 95% confident that the true relative risk falls between 1.5 and 7.9. Another kind of which introduces kind of how we interpret our results goes kind of back to how we look at whether or not a relative risk or odds ratio is significant. And remember, if it includes one, we consider that not significant. So if the confidence interval also includes one, we would interpret it as it's not a significant odds ratio, or it's not a significant relative risk. And we hadn't talked about that before, but it is important, especially if you're reading papers, because you can really, look at that immediately and actually determine whether or not the results were significant or not. So speaking of significance, they can mean different things in different settings. So we can have clinical versus statistical significance. So while small differences in disease frequency or low magnitudes of relative risk may be significant, they may not have any clinical significance. And kind of on the other side of that is with small sample sizes, large differences or measures of effect may be clinically important and worthy of additional study. So this is where statistics and you know even on the epi side, but from a biased perspective, I would say where math aren't you can get all the data you want, but it's important that context is also included in that, because if you look at numbers alone, it might show that it's not significant, but that doesn't mean it's not helping people in a clinical setting. And one example I was actually thinking of a little bit earlier was, we're dealing with this pandemic right now, and a lot of you know, researchers and doctors are trying to figure out new treatment approaches or refurbish old treatment approaches for this novel virus. Um, if a study were performed, and likely, it'll be a smaller sample size, uh, if we administered a certain type of treatment and we saw that people started to improve, and just imagine there was only a sample of 30 people enrolled in this study. A sample size of 30 is very small. You likely will probably get a non-significant result. But what you can't argue is that maybe of those 30 people, 25 people recovered or they improved. And so that's where this is a scenario where, it may not be statistically significant, but clinically it actually does mean something. And maybe we want to design a bigger study from those results. Um, so statistical power allows us to demonstrate whether or not an association exists and if an association exists. So this is determined by the frequency of the condition under study. This will also help us determine what type of study design we'll use, the magnitude of the effect, and then the sample size as well. So there's 5 questions that we should be kind of running in our head when we're designing and evaluating epi studies for their association or the measure of effect. So the first question would be, could the association have been observed by chance? And we determine this through the use of various statistical tests depending on um, the type of data that are actually being collected. Um, the second question will be, could the association be due to bias? Which I'm going to talk about a little bit later. But bias could be systematic, it could be random, it could be due to how the data is collected, or something else is going on as well. Um, could other confounding variables have accounted for the observed relationship? We're going to talk about confounders today as well, which is another type of bias. Um, to whom does this association apply? So this kind of goes back to whether or not our study sample is representative of our actual target population, or if we're trying to generalize these results to, an entire population, just say the entire country, or, all Americans or something like that. Um, if we didn't actually get a representative sample, we can't make those inferences or generalizations, as well as participation rates. And then the fifth question is, does the association represent a cause and effect relationship? And this goes back to causality, which, remember, we think about cohort studies, or if we can look at randomized control trials, we can start looking to see if there are causal relationships. So, and so associations can be, again, they might be not statistically associated, or they could be statistically associated. Um, and when we're thinking about statistical association, these can be either non-causal or they can be causal. And within causal, they can be both direct or indirect. Something else that we haven't really um, focused so much on this semester in class, but it's also just, you know, with a lot of outcomes, I'm looking at diseases, aside from certain rare diseases, there are usually multiple causes. And when you're running statistical models, there are ways to what we call adjust for different maybe confounding factors or other influencers to see a direct relationship between our exposure of interest and that particular outcome. And so these are what we refer to as being multifactorial. And it's a requirement that more than one factor be present for the disease to develop. So now I'm going to actually switch from measure of effect, which some of these things we had talked about a little bit woven throughout the semester, but kind of got it, you know, in terms of thinking about it or applying it to how we're going to approach data and interpret research results. I'm going to shift to data interpretation issues. So, kind of being, very not critical, but just, cautious when you're interpreting data or things to look out for, things you should consider when you're actually looking at results or reading papers. So the learning objectives for data interpretation issues that we're going to go through today, we're going to differentiate random versus systematic errors, go over what that means, state and describe sources of bias and different types of biases, identify techniques to reduce bias, define what's meant by the term confounding, and I'm going to provide a few examples, and then I'm going to describe methods to control confounding. So validity of study design is something that's important when we're actually, when we read a study and, you know, this isn't going to be listed on the study. It's not going to say that this is a valid study or it's invalid. I mean, theoretically, papers that are published hopefully have what we call rigor and, are honest. There are no falsified results or anything like that. But it ultimately is actually up to the reader to be able to look at the methods, look at how they sample participants and all those different things and be critical and kind of, wary to a degree to not just try to attack people's work, but just you don't want to be citing, you know, poor science, I guess, which is not the best way to say it. But um, so this is a degree in which the inference drawn from a study is warranted after accounting for the methods, representativeness of the study sample, and the nature of the population from which it was drawn. And kind of bringing this back to what we're going on with right now, what's going on right now with COVID. I know kind of early on people were talking about like, how our blood type might actually impact our likelihood of actually getting not getting COVID, but actually having severe cases of COVID. And I read a paper that was really what people were referring to, and after reading kind of the results, it wasn't exactly that clear cut and simple, but I forget which news outlet actually, a journalist read this paper and actually just ran with that title because it was going to throw some information and make people react. And so that was just an example, I think, in my mind of sometimes how it's up to, you as epidemiologists and, researchers to really be critical when you're reading studies and interpreting those results. Because ultimately, it's really up to you of how actually, you will and more or less interpret it. Just because it's put out there, it might not actually be exactly all that's what's based on what's reported. Um, so types of error, as I mentioned, they can be either random or systematic. Um, and it's another visual just to show random versus systematic error. So imagine that you had a crossbow or bow and arrow, and you were aiming at a target, practicing archery or something like that. On the left, every time you shot an arrow, it kind of went off to the target over to the left, but it's all clustered in one area. So that would be an example of a systematic error. Um, there's something that that person is doing that is very precise because it's in a similar area. You can see all those dots on the left are basically a line, but they're far away from the center. Then on the right, if we did the same thing, a person shooting the arrows and still not hitting the target, but they're all over the place, and that's what we refer to as random error. So random errors reflect fluctuations around the true value of a parameter because of sampling variability. Factors that contribute towards random error can include poor precision, sampling error, and variability in measurement. And kind of go through each of those individually. So poor precision, it occurs when the factor being measured is not measured sharply. It's similar to aiming a bow and arrow, as I mentioned, at a target that's not in focus. So, opposed to the left, which is pretty precise, they're all clustered around one area. We have these bows and these arrows that are all over the place around the target. Precision can be increased by increasing sample size or the number of measurements. And sometimes you'll see, I just know from experience, when you're collecting data on things like weight or height, sometimes even blood pressure, um, the researchers or the investigators will actually put in a protocol for the person collecting those data to take, weight or blood pressure 2 times or 3 times, and then average what they get, because I'm sure everyone's been on a scale before, especially if you're using a digital scale. That number might change a little bit, and while little changes might not seem that big of a deal, if you get enough of those small changes, eventually things could be way off, and that can shift your results and how you interpret things. So it's just important to kind of take those things into consideration. So sampling error arises when obtained sample values differ from the values of the target population. So this will be an example of this will actually be, if I wanted to just say I designed a study to actually understand the knowledge, attitudes, and beliefs of New Yorkers on, MTA, using the train or the buses. Just their views on how efficient it is and whether or not they, think it's great or not. But within that study, imagine I only actually spoke with people who lived in Midtown. And I did my study. I collected the data. I ran the results, and people in Midtown basically were like, "Yeah, the train is great. Like, I don't have any problems with it. I'm always able to get on it." A key problem would be that I'm only getting the views of people in Midtown, which would not be representative of all the 5 boroughs, let alone within different areas. And so, how we sample and recruit and enroll people into studies is that the data from that can only be as good as a job that we actually do in terms of getting a representative sample. Although there's no way to prevent a non-representative sample from occurring, increasing the sample size can reduce the likelihood of that happening. So in general, a bigger, a larger study sample is usually a good thing, but the problem is it's expensive and it costs a lot more money, and it's more timely to have a lot more people enroll in the study. So it's really important to do a really good job in terms of trying to have as representative of a sample as possible. The last random error can occur from variability in measurement. So the lack of agreement in results from time to time reflects random error inherent in the type of measurement procedure employed. This could be based on inconsistencies in tools used for measurement or a lack of standardizing the tool. Um, Blood pressure, again, is another example of this. So just imagine, it's whatever study, a heart study. And, some nurses are taking blood pressure using an electronic blood pressure cuff, and others are actually taking it with, the manual cuff with the stethoscope. Um, it's likely not only will people get different results measuring the same blood pressure of that individual doing it manually if you got five nurses and did it, um, but those results are probably way different than the electronic blood pressure cuff. So, this will be important in terms of, in the protocol, kind of embedding that all blood pressure is going to be taken using, a blood pressure cuff. Or if we go, we start talking about self-reported, becomes a whole, different issue when you have participants report, height, weight, different things like that. And one thing that, a lot of people probably can relate to, most people usually overestimate their height and they underestimate their weight. And so if you're getting self-reported results and using that as the data, it definitely is going to bias your results. So I'm going to start with this quote when thinking about systematic errors or bias. So deviation of results or inferences from the truth or processes lead to such deviation. Any trend in the collection, analysis, interpretation, publication, or review of data that can lead to conclusions that are systematically different from the truth. And we're going to go through kind of that last sentence, kind of each of those dissected a little bit into different types of biases that can arise that are systematic errors. So factors that contribute towards systematic errors that we're going to focus on are selection bias, information bias, and confounding, which is another type of bias, but it just has its own name because there's a lot of attention that confounding gets. So selection bias. And we think about this in the context of us actually designing a study. So imagine all of us are actually designing a research study. It could be that same study that, we want to look to see the knowledge, attitudes, and beliefs surrounding, MTA use in New York City. And we're going to, basically enroll people who live in Midtown. And so that first kind of example of only enrolling people in Midtown, but wanting that to be representative of New York City and all five boroughs will be a selection bias. And so it refers to distortions that the result from procedures used to select subjects and from factors that influence participation in study. And so selection bias is not only, you selecting certain people in, in Midtown, for example. It could be maybe that you actually are only, enrolling people in the study who live in Midtown who have iPhones. And so, by restricting it to people who have iPhones because they can use iMessage, you're actually going to, basically make a lot of people ineligible, and it's probably not going to be, it's going to be even less representative of New York City. Selection biases can arise when the relation between exposure and disease is different from those who participate and those who theoretically would be eligible for the study but do not participate. So an example could also be respondents to the Iowa's Women's Health Study. So these people who participated in this study were younger, way less, and were more likely to live in rural areas, less affluent counties than the non-respondents. And so this really, if this study were supposed to represent Iowa, it would actually really only be representing the rural part of Iowa, looking at lower socioeconomic status, and not the entire state. So in terms of reducing our likelihood to fall into selection bias, we want to develop explicit case definition or who we're actually going to be classifying as being eligible. You want to enroll all cases in a defined time and region. Strive for high participation rates and take precaution in terms of ensuring representativeness. So, you know, one selection bias that always used to come up when I was taking epi classes was the fact, and this is something that will be included in someone's limitations if they're writing a study, and if they, you know, they don't mention this, it kind of becomes a problem. Is that usually people who are institutionalized, meaning that you're incarcerated or there's a psychiatric hold, a mental institution, people who are in nursing facilities, those people are not usually going to be included in your studies, and so it's always going to be some type of limitation or always some type of bias that's going to be exist within your study, because if you're trying to represent an entire community or entire country, those people also are residents of this country, and so by excluding them, which is a lot of people, you just have to be cautious in terms of how you're interpreting it, or at least acknowledge that that is a limitation with your study. So next, I'm going to shift to information bias. And this is basically in the name, it's a bias based on the information that you receive. And so it can be introduced as a result of measurement error in assessment of both exposure and disease. And there are a few different types of information bias. So recall bias is one example. Um, and this is better being able to better recall data or information among cases compared to controls. Uh, so take Zika virus, for example. Zika virus, I know it was on the exam, is a type of virus, there was an outbreak in 2015, 2016. And so, it was a vector-borne uh, infection that was spread through mosquitoes biting people, basically. And we saw the microcephaly, which is this abnormally small head among newborns. And so, one type of information bias that actually could be introduced in terms of studying Zika virus is that it's more likely that women who gave birth to children with microcephaly, if you ask them, did you get bitten by a mosquito, or how many times you got bit by a mosquito during your pregnancy, they're likely going to remember or try or recall that information, just because at that point they are a case, they have a child that actually has this condition, versus a woman that gave birth maybe in that same region, who did not have a child with microcephaly. She probably wasn't really thinking about the mosquito bite or having been bit by a mosquito, if you went and asked her the information. We also have interviewer bias. So this can occur when interviews probe more thoroughly for an exposure in a case, compared to a control. So one example of interview bias. And so if you knew, for example, that again someone had microcephaly, and that they're a case in your study, you're probably going to really, and the woman's like, I'm not really sure if I got bit by a mosquito, and then the interviewer might start to kind of go off script and start asking, well, do you remember having any kind of bug bites, or maybe were you itchy during the time of your pregnancy, and trying to probe for more information, and that's going to bias the results that we actually get. Um, then we have lion bias, which occurs when participants have ulterior motives for answering a question and thus may underestimate or exaggerate an exposure. And another example, just kind of what I gave earlier, is that maybe someone, if you're asking someone about their height and weight, they might, not accurately report their height or weight, just because, people usually underreport their weight, or, report a lower weight, or overestimate their height. And so, that can introduce a different type of bias. Or in, another way where someone actually just might not feel comfortable. I know, when you start to talk about, there are studies that look at people who may use injection drugs, or maybe people who are having higher risk sexual behavior. If you start to ask about, people's how many sexual partners they had in a certain period of time, or how frequently do they inject drugs, if they inject drugs at all, it becomes important that the researchers have a very established rapport with those participants, because if you ask a lot of people about sexual partners or you ask them about drug use, most people are probably going to say they don't probably don't use drugs, and they might underreport in terms of how many sexual partners they're having. But that could actually start to introduce this bias into the study and the interpretation of the data. So, in terms of reducing information bias, sometimes you can blind the interviewers, meaning that the interviewers don't know whether someone's in an intervention group versus control group, or if they're a case versus control. You can provide standardized training sessions and protocols. So, retrain your interviewers to, not go off script. That's something that became very important. If you've ever worked on a research study, or when you will work on a research study, is when those questions come up and you're actually asking the participants, especially if it's using this computer assisted software interviewing software, you have to read those words verbatim and make sure that the person answers the answer choices that are provided, instead of something else. Um, Use standardized data collection forms. You can sometimes blind participants about the study goals and classification status, although that's not usually something that happens as much. Aside from, sometimes people might they might have the placebo versus the actual intervention for a control trial. And then you want to try to ensure that the questions are clearly understood through careful wording and pre-testing. So, confounding. I've kind of thrown this word around a little bit before in the semester, but we're kind of going to walk through what confounding is and why this is important. So, confounding refers to the distortion of the estimate of the effect of an exposure of interest because it's mixed with the effect of another factor. This occurs when the crude and adjusted measures of effect are not equal. We're not really doing this in this semester, but if there's a difference, you really usually look to see if there's a greater than 10% difference between what we consider what would be the crude versus the adjusted measures of effect, whether that's odds ratio or relative risk. And by doing that, we can actually control for this in our data analysis. We'll provide a visual that hopefully makes it a little bit more clear. So, this is a visual representing confounding. So we see on the left the exposure. This can be, I don't know, maybe it's coffee consumption. And we also see the disease on the left could be tachycardia, which is an abnormal heart rhythm. Um, a confounding factor that might actually be in the middle could actually be, hypertension, for example. So if we were actually looking at the association between, you know, coffee consumption and, having tachycardia, hot, or abnormally fast heart rhythm, if we only want to look at those two things together, we would have to account for things like hypertension or other things that we either know about based on doing a literature review, or that we tested statistically to see if it was a confounder. Because by doing that, we can actually just basically close off that confounder, or just kind of mute it and look at the true relationship between coffee consumption and tachycardia. This was an example that I actually provided from, it was a conceptual model for my dissertation, but I see that it's not coming up, so I'm gonna go past it. But just in general, it was just showing that I was looking at chronic stress and cardiovascular disease, and there are multiple things that, factors we know are risk factors for cardiovascular disease. So it will be important to basically identify those and control for those, or adjust for those in my statistical analysis, because if I don't do that, there's no way that I can look at, you know, my particular exposure and cardiovascular disease as an outcome alone, because there are going to be a lot of interferences going in the way. Something else I actually forgot to mention, that usually the reason why it's also important, in terms of adjusting for identifying and adjusting for confounding, is that by not doing so, we basically will probably overestimate our relationship between our exposure and disease. So we might get a odds ratio if we didn't adjust or we didn't account for certain confounders. We might get an odds ratio of 8 for coffee consumption and tachycardia, but after we actually adjust for all the different confounders, we might only see that there's a 2. The odds ratio may only be 2. So to be a confounder, another factor must satisfy the following criteria. So it must be a risk factor for the disease. It must be associated with the exposure. And it cannot be an intermediate step in the causal pathway between the exposure and disease. So, well, before I get to the other example at the bottom, so one example will be air pollution and bronchitis. They're positively associated. Both are influenced by crowding, which is considered a confounding factor. So if we were doing a study and looking at air pollution and bronchitis, we would probably adjust, or we would adjust for crowding, or ask a question about crowding so that we can adjust for that in our analysis. Another example would be looking at physical inactivity and heart disease. And so just imagine we wanted to see whether or not people who exercise less than 1 time a week had an increased likelihood of developing heart disease. Well, one confounder we know, or one thing that we know that actually influences both physical activity and heart disease, is age. And remember, aside from congenital birth defects with heart disease, most people don't develop heart disease until 50 and older. So we would have to actually adjust for age, which you might see this a lot as age adjusted, odds ratio. Age is after adjusting for age or accounting for age. It's because those researchers and statisticians, they knew that age was a confounder for that particular outcome and exposure. So how do we control for confounding? So we have some different ways that we'd actually approach for adjusting for confounding. Their prevention strategies. So this is when you attempt to control for confounding through the study design itself. And 3 different types of prevention strategies. One of these we actually talked about is randomization. So by randomizing, you have kind of this fair shot of having, people in the control and intervention groups. And so, basically those those small little differences could almost in a way cancel each other out at some stage of the actual study itself. We have restriction, which I'll talk about soon, and also matching. And in terms of on the analysis side, we can use stratification and multivariate techniques or modeling. So with randomization, we're attempting to ensure equal distributions of confounding variable in each exposure category. Advantages include that it's convenient, inexpensive, and it makes the analysis pretty straightforward. But the disadvantages are the need to control over the exposure and the ability to assign subjects to study groups. You also need a larger study sample to randomize. So in terms of restriction, it may prohibit a variation of the confounder in the study groups themselves. So for example, if you restrict the participants to a small age category, you can eliminate age as a confounder. So going back to looking at physical inactivity and heart disease, if we did that study and we didn't want to have to worry about age, instead of including people who are 18 and up, we might actually want to only focus on anyone enrolling in their study might only be 45 to 80, or maybe 45 to 70. Because in that point, you actually wouldn't have to adjust for age likely, but you would report based on different age intervals because you want to see if there are differences by age kind of group. And it's usually clustered in a range, probably no more than, if in this case, it would be probably 45 to 50 or no more than 45 to 55 as one, age group. This provides complete control over known confounders, and unlike randomization, cannot control for unknown confounders. Then we have matching, which we haven't talked about at all, but it's something that you should know that exists. And this is when subjects are matched in a study according to the value of suspected or known confounding variable to ensure equal distributions. So we can do frequency or individual matching. Frequency matching occurs when a number of cases uh, with the particular match characteristics is tabulated. Or another way of thinking about this is actually if we knew that um, our exposure, that all the cases had a similar, exposure or a similar frequency of that exposure, we want to match. We may want to match on, that as our, our variable, or we might choose another variable that we know other people may have in common that could be, a confounder between our exposure and outcome of interest, and we want to match on that. Um, then we have individual matching, which is basically similar to that, but we're just picking like sex, race, or marital status, something like that, some social uh, um, demographic variable that we actually are just just going in, and we're just going to match on that to control for confounding. So advantages include fewer subjects are required than in unmatched studies with the same hypothesis, which can enhance the validity of follow-up study. Disadvantages include that it's costly because extensive searching and record keeping are required to find the matches. A lot of when you will see match when you're analyzing the data with a match on with matching, it's usually not usually, but a lot of times you'll see it retrospectively. So the data are already collected. Maybe it was data from a national survey or something like that, and you actually just went and matched and before you did your analyses. So in terms of the analysis, ways to control for confounding, we can use stratification or multivariate techniques. Um, Stratification includes happens when analyses uh, performed to evaluate the effect of an exposure within strata levels of the confounder. And strata basically you could think of, if thinking about age for again as an example, if we had the same study of, we're looking at heart disease and physical inactivity as being our exposure, heart disease being our outcome, and we knew that, we're only going to include people who are 45 to 70 because we know age is a confounder. Um, we can actually assess confounder, further assess confounding by actually breaking people down into smaller age ranges like 45 to 50, 50 to 55. And each one of those are considered a level or a strata, and that's a way we can actually test for confounding. Then we have multivariate techniques or modeling, in which we use computers to construct mathematical models, and they can describe simultaneously the influence of exposure and other factors that may be confounding the effect. Unfortunately, we won't do this in class this semester, but these are the models that actually produce the results you see in publications. Um, this is how you actually, basically run your analyses after you collected your data, because there's no way that you can do, well, you could do this by hand. Someone used to do this by hand a long time ago, but there are just some very great software out there that we can basically organize and clean our data, and basically run analyses, and it'll give us odds ratios, it'll do the statistical tests, all these different things we need to generate the data, and then from there we can actually interpret those and report those and produce papers and publications. So in terms of advantages of stratifying, um, performing analysis within Strata is a direct and logical strategy, so it's pretty straightforward. Minimum assumptions must be satisfied for the analysis to be appropriate, and the computational procedure is pretty straightforward. Disadvantages include small numbers of observation in some strata. This is actually, if you've worked with data, or just letting you know when you work with data in the future, this becomes a really big problem, because when you're running those, if you're doing these models or running these mathematical models, looking within strata on a computer software, statistical software, if there are a small amount of observations in one group, it's going to throw off everything, or it might not actually even run the analysis. So this becomes, issue that comes up a lot, actually, especially when I think about race, ethnicity, because the further it gets broken down, usually there are fewer people in certain groups or subgroups. Other disadvantages include a variety of ways to form strata with continuous variables. So, and a continuous variable will be, age, for example. Um, so, how do we categorize, age? Are we going to just look at everyone who's, 20? Or are we going to put people who are 20 to 25 together? Are we going to put people 20 to 30 together and make it, what we consider a categorical variable? So that becomes a little bit tricky. It's difficult to interpret when several confounding factors must be evaluated. And categorization results in a loss of information. So by taking, age, for example, putting people, looking at all 20-year-olds or 21-year-olds, and we look at people who are 20 to 30, there are going to be some differences in that age group. And so that might actually be helpful if we put them together, or it could actually hurt our results and interpretation of those results. And so all these things are really, it's up to the investigators to really, really understand their topic and do their research in terms of how they're going to be categorizing all these different things that we've talked about. Because as you can see, you can have the same data, and when you go to run your analyses, you can put people in groups or look at them as an individual, in terms of an age, and that's going to mean something different in terms of the results you get. So in terms of multivariate techniques, advantages and disadvantages, advantages include continuous variables do not need to be converted to categorical ones. It allows for simultaneous control of several exposure variables in a single analysis. Although you will do multiple iterations of the models, it just won't be one model you do and then that's it. You usually play around with construct multiple models and run them to see, they're consistent, different things like that. And disadvantages include potential for misuse. So there are a lot of different type of models or multivariate models you can use. It is also up to, you can have the best data in the world and not, you're an analyst or whoever's analyzing your data did not choose the appropriate model to run your data on, and you're going to get way different results. And, whether those results came as being even significant or true when it comes to generating a paper, the reviewers are going to look and say, why did you use this model over this? And or that wasn't the appropriate model to use. So this is where the person has to be an expert in terms of knowing which type of model is even appropriate to analyze the data, even though they have, great data already. So the last bias that I'm actually going to talk about, which is also another bias that was stressed, in epi classes, just like selection bias to me, was the publication bias. So this occurs because of the influence of study results on the chance of publication. Studies with positive results are more likely to be published than studies with negative results, and may result in a preponderance of false positive results in the literature, which is a big issue. Bias is compounded when published studies are subjected to meta-analysis. So another kind of comment on this is that, and this this always comes up actually, is that people want, when you run it, when you do studies or you know analyze your data, everybody wants to get positive results or favorable results. Nobody wants to get, they do this study, they spent $100,000 over the course of 2 years, and then they come and do their analysis to say what we did, our intervention didn't work. Nobody wants to get that news, but it's important that that actually is published because it helps other researchers to understand that this doesn't work. So we're not going to do this, or we're not going to spend time or effort in order to try to, produce that same study. Instead, how can we learn from what they did so that we don't kind of fall into that same, thing? Unfortunately, and this is kind of a caveat in academia, publishing papers is a big thing, and especially, having favorable publications. And so people might actually be hesitant to actually publish negative results. And so that's where this publication bias comes in, is that people basically only things that are published are usually some type of favorable or positive results instead of the negative results. And there are plenty of bad, not bad, but just studies that, interventions that didn't work or had negative or unfavorable results that just weren't published. And then we also have, this this not willingness, but attempt to, sometimes people will kind of fizz their data a little bit, which, I mean, it happens. The thing is, when people get caught, they get, it becomes a big thing. So, and there's records, I forgot where this is housed at, but basically people, when they found out that they falsified their data, or falsified their results in order to get published, people lose their license. You can get fired. Like, a lot of there's always going to be some type of penalty that happens with things like that. And one example that actually comes to mind with this actually is the vaccine. I forgot the person's name, but there was a doctor who had to study on vaccines and autism, who basically concluded that vaccines cause autism. He actually, the paper got published, but people, kind of really investigated that, and they found out that he actually falsified the results. So they pulled his paper. I think he might have lost his license, but I mean, you definitely get like on this list of where you can't even apply for grant money. You probably will either lose your license or it gets suspended. You may lose your job or get put on administrative leave. So it becomes really, really serious, because at that point you're lying. You're using your position basically to lie, and that's just not what what we want to do. So to kind of summarize a little bit of what we talked about today, we talked about measures of effect, um, which are a quantity that measures the effect of a factor on the frequency or risk of an outcome. And when we switched it to talking about interpretation issues that arise, mostly about different type of biases and errors. So we talked about systematic versus random error, and within systematic error, we have selection bias, information bias, and then it's confounding. Also talked about ways that we can account for that or try to prevent or reduce our risk of running into those type of issues. Um, so this is actually kind of this turning point in the semester, where we just kind of switch from talking about study designs. Today we talked about different type of measures of effect, which we had spoken about in class before, but more importantly, data interpretation issues. And then for the rest of the semester, we're basically gonna kind of focus on areas of specialized areas of epi. So infectious disease epi, social epi, different things like that. And at the very last class we have is we're gonna focus on ethics, and so ethical considerations. We're talking about research, and kind of what we learned from the past, and so what we know not to do and what's considered unethical. Again, hopefully everyone stays safe and healthy. Hopefully everyone has the things that they need. Definitely feel free to reach out to me if you have questions, concerns, as some of you, things might arise in the, going forward.